Let's take a look at another example. Wendy took a trip whose total distance was 80 miles. She traveled part of the way by bus, which arrived at the train station just in time for Wendy to complete her journey by train. The bus went 25 miles per hour and the train went 60 miles per hour. The entire trip took 1.5 hours. How long did Wendy spend on the train? So the previous question, it's a little easier to separate the two journeys because it was two different people on bikes. Now it's one person, and the way to think of this, how do we split this up? There was the bus journey, and then immediately after there's a train journey. Now normally you don't take a bus and right at that moment you're not able to hop on the train right away, but we're just doing that to hopefully simplify this just a little bit. And here's the thing: the distance on the bus plus the distance on the train all together adds up to 80 miles. This is given away by the first sentence saying took a trip whose total distance was 80 miles. So it's not 80 miles on the bus followed by another 80 miles on the train. That'd be 160 miles total distance, right? So we don't know how much the bus journey distance was or how much the train journey's distance was. We don't want to assume it's 40-40 split each, right? As half each. We'll just say the distance on one vehicle and the distance on the other vehicle added together is equal to 80. The time on the bus plus the time on the train equals 1.5 hours, right? So here the times add up. In the previous question, remember the experiment in the previous question was the two cyclists start at the same time and they stop their pedaling when they right at the moment they meet each other. So that in the previous question the times were equal. In this question, the times add up to 1.5, a number given in the problem. So let's take a look at what we have. Um, we we don't know the bus distance or train distance, so we'll use two separate variables. I just call them D and C. We don't know the amount of time on the bus or the train each individually. We'll just use T and U. So we just know that D plus C has to add up to 80. We just know that T plus U has to add up to 1.5. The rates, the speeds are given in the problem, so no need to introduce a variable there. We just put in the 25 and the 60 in this table. So applying the distance formula to the bus journey, we have D is equal to 25t. Applying the distance formula to the train journey, we have C is equal to 60 times U. We also, it's already mentioned kind of up there that the bus distance plus train distance equals 80. Now we can write that more in symbols as D plus C equals 80. Similar with the times add up to 1.5, that will be T plus U equals 1.5. So what we can do is take in the previous lines, solve for C, right? C is 80 minus D, and then solve for U, for instance, subtracting T on both sides. So U is equal to 1.5 minus T. And then we can take 80 minus D. So we can take this equation, there's lots of options, but we can take C equals 60U and replace the C with 80 minus D, so that's what's on the left side, equals, copy the 60, and then the U that appears it was 60 times U, replace the U with 1.5 minus T, of course in parentheses. So then we can distribute the 60 on the right side, so 80 minus D equals 60 times 1.5 minus 60T. And then if we take that equation and all we do is replace the D on the left side, so it says 80 minus D, instead we write 80 minus 25T. Now you have an equation that's just in one variable, T, right? 80 minus 25T equals 60 times 1.5 minus 60 times T. So let's take that to the top of the next slide. And then we'll add and subtract things on both sides to get all the terms with t on one side and all the terms without t on the other side. So you'll see that from the first equation to the second equation, what happened was adding 60t to both sides and subtracting 80 on both sides. So now just all the number stuff with no t is on the right, and then the terms that have t are on the left. Now we can factor out t on the left. You might just want to think of collecting like terms, and that would be fine, but I think it's good as a reminder here to say what collecting like terms really is factoring out the variable, and then divide both sides by what's in parentheses on both sides. On the left side, you have a 60 minus 25 times t over 60 minus 25 times 1, so we can do that cancellation. We're left with t is equal to that fraction, 60 times 1.5 minus 80 all over 60 minus 25. Now that, without worrying about simplifying here, that's t, that's the time on the bus. However, the question asked how much time on the train, which was u. So earlier we saw that u is equal to 1.5 minus t. So all we do is u is equal to 1.5 minus, and we now have this ridiculous looking fraction, but it's just numbers. That was t, so we replace that. Our conclusion, we'll say that Wendy spent 1.5 minus 60 times 1.5 minus 80 all over 60 minus 25 hours on the train. And we won't bother simplifying this any further. I really am not interested in having people type this kind of thing into a calculator. The online homework will just take answers that look like this anyway. So don't bother. Just keep it like that. Okay, as an alternate method, and you might prefer this method, you might not, but it's sort of the same idea of if you want to try to do this with fewer variables. So we'll use some of the same variables as earlier. So d is the distance on the bus, t is the time spent on the bus, and then we haven't created variables for the distance or time for the train journey yet, and they've just been called this and that in yellow and green. So because d plus this has to equal 80, this is still applying the principle that the two distances in this problem had to add up to 80 total miles. We can get that this is equal to 80 minus d. And then same deal with the time, right? So the time that's unknown t plus the time on the train, which we're just calling that for now, had to add up to 1.5. So if we solve for that by subtracting t on both sides, we have 1.5 minus t. And so we can update this table to really be the distances are d and 80 minus d, and the times are t and 1.5 minus t. Okay, then with that setup, this is perhaps a bit nicer for folks just because there's fewer variables. You apply the distance formula, and you have d equals 25t, and you have 80 minus d equals 60 times 1.5 minus t. So two equations and two variables. Your next step here would well, there's lots of options, I guess, but I think the easiest next step is, since you have d equals 25t, so d is already isolated on its own, why not replace d with 25t in the other equation? So you have 80 minus 25t equals 60 times quantity 1.5 minus t, and that equation is now just all in one variable, so it's fairly nice. A couple other comments, I guess, is that you should practice this method, but when you get comfortable with it, you'll just kind of perhaps get to a point where you don't write like d plus this equals 80. You might just stare at your table and say, oh, if one distance is d, and I know the two distances need to add up to 80, the other distance should be 80 minus d. Same deal with the time. Okay, so if we just compare the two methods that we had here, in the earlier method, we just had many more variables, and some people prefer this approach, and it's fine. But just to compare and connect the two methods, either you create distance variables d and c for the bus and train, and time variables t and u for the bus and train, and you do things like, say, d plus c equals 80 and t plus u equals 1.5. So then when you solve for c and u, the distance on the train and the time on the train, you get things like c is equal to 80 minus d and u equals 1.5 minus t. Or you do method 2, which is, instead of introducing a variable called c, you just, before creating that variable, just take a moment and go, wait a second, d plus whatever I put where the yellow box is would need to add up to 80. And so that should be d added to 80 minus d. That's what would add up to 80. It's the same 80 minus d that you see here. I'm trying to use the color to help. Same argument for the time. If it's t, an unknown time called t, plus we don't know what, but what should even fill this box that's highlighted green? Well, t plus whatever we fill the box with needs to add up to 1.5. And the thing, t plus what adds up to 1.5? Well, that what here would have to be filled with 1.5 minus t. These methods essentially are the same. It's just a matter of, do you create four variables by not replacing c early on and just saying things like d plus c equals 80, or do you, before you create a variable called c, just take a moment and go, what would have to fit in the table here so that I have d plus whatever I fit in the table would add up to 80. These are essentially the same. In both methods, the distance of the two journeys adds to 80, and in both methods, the times of the two journeys adds to 1.5. And that is key, is to look at the question and go, do the distances add up? And based on how the problem reads, the two distances in the question should add up to a given number in the problem. It was 80, and it's just a matter of which way do you write this down, with two variables that add up to 80, or one variable and then an expression that uses that same variable somehow with an 80 minus d. Okay, so again, just in summary of what happens, you have two journeys, therefore you have two distances. Your two distances can be equal in some problems. The two distances two distances can add up to a number given in the question for other problems. Again, you have two journeys, so there are two times, and the two times might be equal, or the two times might add up to a number given in the problem, or the one journey's time might be obtained from the other by adding a number given in the question. So we saw distances add up to a given and the times equal. That was the cyclist's problem. We saw that the distances add up to a given and the times add up to a given. That was Wendy on the bus, then the train. So for an interactive question, I'd like you to, this is challenging, so do your best, but I'd like you to design your own word problem. You just make the question. You don't have to answer the question, but design your own word problem where the two journeys' distances are equal. We haven't had that example. So far we've had distances add up to given, right? And then explain if you to take it a little further, it helps you kind of correct for just in case your first thought might or might not work. Explain why the two journeys in your problem should have equal distance.